Recording has started.
Let's see how you're doing on these. I realize you may not have had time to finish all of them, but let's take a peek. So for the first one here, metric conversion, we just have our main unit in the middle. For in this case, it's grams. Then our prefixes go out from each direction. Going smaller, it's decigrams, centigrams, and milligrams. Here we're going from milligrams to grams, which on the chart is 3 spots to the left. So we move our decimal point 3 spots to the left. Well, in the number, there's no decimal point written. That means it's at the end of the number. Now we move that decimal point 3 spots to the left. 1, 2, 3. It is 0.72 grams. For the second one, we have 5.3 grams per centimeter squared going to kilograms per meter squared. So remember, that is 5.3 grams over 1 centimeter squared. And since both of these are metric units, we don't have to use a conversion factor. We can just move the decimal points and then divide it out. So we're going to turn the grams into kilograms. Finishing my chart here, we would have decagrams, hectograms, and kilograms going this way. So going from grams to kilograms is 3 spots to the left on the chart. So my decimal point has to move 3 spots to the left. So we go 1, then we have to add zeros for 2 and 3. So that is 0.0053 kilograms. And then we also have to go from centimeters squared to meters squared. So if we put meters in the middle here, from centimeters to meters is 2 spots to the left, but it's not just centimeters and meters, it's squared. So since it's centimeters squared and meters squared, every spot on the chart is 2 decimal places. So that 2 spots on the chart means my decimal point has to move 4 spots. So there's no decimal point there, which means it's at the end of the number or after the 1. So we go 4 spots to the left. We go 1, and then we have to add zeros, 2, 3, 4. So that is 0.0001. We divide that out. 0.0053 divided by 0.0001 is 53. That'll be kilograms per meter squared. So 5.3 grams per centimeter squared is 53 kilograms per meter squared. Next, I wanted to go between standard and metric a little bit here. So 132 pounds. We'll put that over 1. We do have to use the conversion factors now. We're going to put pounds on the bottom so we can cancel out, kilograms on top. 1 kilogram is 2.2 pounds. So the pounds cancel out. 132 times 1 kilogram is 132 kilograms. 1 times 2.2 is 2.2. 132 divided by 2.2 should be 60, and it is. So that is just 60 kilograms. Number 4 here, we have 20 pounds per square inch. That's 20 pounds over 1 square inch. I have to convert the pounds into grams and the square inches into square centimeters. We're going to have to use our conversion factors here. Now, I don't have a direct conversion from pounds to grams, but I do have pounds to kilograms. So let's do that. 1 kilogram is 2.2 pounds. Now, you could probably look up a direct conversion from pounds to grams as well. I'm just choosing to use that one because I have it memorized. Now, to get rid of the inches squared, they're going to go on top, and we're going to centimeters squared. We know that 1 inch equals 2.54 centimeters, which means that 1 square inch equals 2.54 squared, or 6.4516 square centimeters. So 1 square inch is 6.4516 square centimeters. Now the square inches cancel out. So we've got 20 times 1 kilogram times 1 is 20 kilograms on top. On bottom, we have 1 times 2.2 times the 6.54 or 4516 square centimeters gives us 14.19. We're going to round that to centimeters squared. Now that is kilograms per centimeter squared. We want it as grams per centimeter squared. So to convert the kilograms to grams, we're just going to move the decimal point. On the chart, kilograms to grams is 3 spots to the right. So I move my decimal point 3 spots to the right. That is 20,000 grams over 14.19 centimeters squared. So I'm just going to take 20,000 divided by 14.19, giving us 1,409.44. So a square centimeter is quite a bit smaller than a square inch, but a gram is extremely small compared to the pound. There is like 420 grams or so in a pound. I could probably figure it out. I did that wrong. There it is. Actually, 454. Okay, that's one I've tried to memorize in the past, but I can never quite remember it. Okay, so for number 5, 12 kilograms per liter. Couldn't have done that one because I labeled it wrong. That's showing kilometers per liter. Going into miles per gallon. So hopefully you didn't get to that one and spend a lot of time trying to convert that because I had my units messed up. But 12 kilometers per 1 liter going into miles per gallon. So let's convert the kilometers to miles. Kilometers are going to go on bottom. Miles on top. 1 mile is 1.6 kilometers. Kilometers cancel out. Now we need to get rid of the liters. Liters will go on top. Gallons on bottom. 1 gallon is 3.785 liters. So my liters have canceled out. On top, I have 12 times 3.785. 45.42. And that is miles. On bottom, I have 1 times 1.6 times 1 gallon is 1.6 gallon. So take my 45.42 divided by 1.6. 28.39, we're going to call that. That is miles per gallon. Any questions on the homework from last week or any of the problems we just went over? So one of the things we did here is we did some conversions with our metric units. You know, things like 2,800 milliliters going into liters. And all it was a matter of moving the decimal point. Liters are in the middle. We have deciliters, centiliters, milliliters. From milliliters to liters is 3 spots to the left. We moved our decimal point 3 spots to the left, giving us 2.8 liters. Now, of course, we had decaliters, hectoliters, and kiloliters in here as well. And, of course, if we kept going, we skipped the 10,000 and 100,000 to go to the million. There'd be microliters. There'd be nanoliters, but that's a little small. We don't typically get into anything that small. Going larger, we skip the 10,000, 100,000. We go to megaliters. And we had mentioned that these units here, like deca and hecto, hardly ever get used for anything. Deci and centi only get used for specialized applications. The ones that typically get used are the main unit, milli, micro, kilo, and mega. So only the thousands and the millions or the thousandths and the millionths. It doesn't matter what unit those are put on. those prefixes mean the same thing. In automotive, you guys do a lot with electricity. Well, you might have an amp, or you might have milliamps. A milliamp means the same, that milli means the same as it would on a centimeter or a milliliter, milligram, or whatever. It is 1/1000th. So 1 milliamp is 1,000th of an amp. Or if we're looking at ohms, if we have a kiloohm, of course, you guys know that upside down horseshoe type thing is the symbol for ohms. 1 kiloohm is 1,000 ohms, because kilo means 1,000. Those metric prefixes mean the same thing no matter what unit we're putting them on. We might have something listed as 24 milliseconds. Well, again, I want to convert that into regular seconds. We have our main unit in the middle. We don't use the deci and centi. This will be our milli down here. Get from milli back to our main unit is 3 spots to the left. Move our decimal point 3 spots to the left. That is 0.024 seconds. In electronics, I'm not so much in the automotive applications, but if you got into more of the telecommunications, computer electronics, you even break down circuits to microseconds. You might have something that is operating 850 microseconds. So I would just add on to this. Micro would be down here. Get from microseconds, or micro anything, to back to the main unit is 6 spots to the left. So I'd have to move that decimal point. If I wanted to convert this to just regular seconds, I move that decimal point 6 spots to the left. That is 0.00085 seconds. So our main conversion for today is we want to talk about temperature. Now, when we talk about temperature, we have a couple of benchmarks. We tend to use temperature at which water freezes as one benchmark, the temperature at which water boils as another benchmark. So our standard system of temperature is degrees Fahrenheit. I'm not going to try to spell out Fahrenheit right now because I'm sure I'd butcher it. But in the Fahrenheit scale, what temperature does water freeze at? Somebody be brave and yell it out.
32 degrees.
32 degrees Fahrenheit. Good. Does anybody know what temperature water boils at? When I was in school, we used to have to memorize this one, but I found fewer and fewer students actually know this one anymore. Actually, 212 degrees Fahrenheit is the boiling point of water. Now, I should qualify this. This is at what we call 1 atmosphere, so standard atmospheric pressure at sea level. Of course, atmospheric pressure varies even at sea level, but these temperatures vary, especially the water boiling varies considerably with atmospheric pressure. A good friend of mine likes 3-minute eggs, and he had it timed down to exactly 3 minutes and 20 seconds that he had to boil them when he lived here to get them to exactly how he wanted. Well, he moved to just outside of Denver, and he was at about 6,000 feet of elevation. So the air pressure was quite a bit lower out there. Atmospheric pressure was very much lower. Water boils at a much lower temperature. Now, by much lower, I'm probably talking 6, 7, 8 degrees maybe. But he cooked his egg for 3 minutes and 20 seconds and opened it up, and it was pretty much still all all runny on. There was nothing hard boiled in it at all. That's because that difference in atmospheric pressure causes water to boil at a lower temperature, so it didn't heat up as much. So when we talk about all these temperatures, we are assuming we're talking at 1 atmosphere, or normal atmospheric pressure at sea level. The metricized temperature scale is the Celsius scale. Can anybody tell me what temperature water freezes at in the Celsius scale? Be brave.
I've got no idea.
No idea? It's actually 0 degrees Celsius. Then water boils at 100 degrees Celsius. So in that Celsius scale between water freezing and water boiling is 100 degrees. Because of that, the Celsius scale actually is sometimes called a centigrade scale. Centi meaning 100, grade meaning divisions. That's because there's 100 divisions between water freezing and water boiling. The term centigrade, they used to say, 30 degrees centigrade. That term has kind of fallen away, and they just use the term 30 degrees Celsius now. But that's where that came from, is 100 divisions between freezing and thawing. Whereas in the Fahrenheit scale, if I take the 212 minus 32, there's 180 degrees between water freezing and water boiling there. There's a bigger issue, though, other than the difference in the size of a degree. The bigger issue here is that there is no common 0 point. What does that mean? Well, that means in length, 0 feet is equivalent to 0 meters, which is equivalent to 0 centimeters, which is equivalent to 0 inches. There's a common 0 point. No matter what unit we're using, 0 is 0. It's nothing. Or 0 grams equals 0 pounds equals 0 kilograms equals 0 ounces. 0 is 0 no matter what unit we're using to measure weight or mass. Or 0 gallons equals 0 liters. Again, no matter what unit we're using to measure capacity, 0 is 0. Here, that is not true. 0 degrees Fahrenheit does not equal 0 degrees Celsius. You might wonder, well, why did they use such weird temperatures? Well, there's a couple of different theories. One is, most of the Fahrenheit scale is actually based on mercury rather than on water, like the Celsius scale. That has something to do with the selection of those temperatures. Also has something to do with the area in which it's in, where they felt 0 was like the base temperature that they could get. It was the coldest they could feel it getting. Either way, we have to somehow account for that. We cannot just use a conversion factor to go from degrees Fahrenheit to degrees Celsius because of that difference in 0 point. They don't have that common 0 point. So in order to convert from one temperature scale to the other, we actually need a conversion formula. Now we're going to have two conversion formulas. One's going to take us from Fahrenheit, convert us into Celsius. The other one's going to take us from Celsius to convert us back into Fahrenheit. Now, they're actually the same formula, just rearranged. So, if I am given the temperature in degrees Fahrenheit and I want to know what the temperature is in degrees Celsius, I start out, F is my temperature in degrees Fahrenheit. First thing I have to do is equalize that 0. Well, there's a difference of 32 degrees between the zeros. So the first thing I'm going to do is take my temperature in degrees Fahrenheit and I'm going to subtract 32 from it. That equalizes the 0 point. Now I mentioned this difference in the number of degrees between water freezing and water boiling. That gives us a ratio. 100 degrees Celsius is equivalent to 180 degrees Fahrenheit. That reduces, both of those divide by 20, to 5/9. So 5/9 is then the conversion factor I would use once I've subtracted the 32 to bring the zeros equal. So let's use an example here. Human body temperature, 98.6 degrees Fahrenheit, is considered to be human body temperature. Let's see what that's going to be in degrees Celsius. So we're going to plug that in here. 5/9 times, for the F, we put in 98.6. Then we subtract 32. So this is simply going to be order of operations. 98.6 minus 32 is 66.6. Now we multiply that by 5/9. Enter that in the calculator. You just do 5 divided by 9 and then times 66.6. Gives us 37 degrees. So 98.6 degrees Fahrenheit is equivalent to 37 degrees Celsius. To go the other direction, if I have my temperature in degrees Celsius and I want to get it in degrees Fahrenheit, well, I'm just going to reverse this formula. Here, the degrees Fahrenheit, we subtracted 32, then we multiplied by 5/9. To reverse that, we would divide by 5/9. Now, the same as dividing by 5/9 is to multiply by 9/5. And then we would add the 32. For our temperature in degrees Fahrenheit, we would take our degrees Celsius times 9/5 and then add 32. Let's say you're driving into work in the morning, and the announcer on the radio says it's going to be 20 degrees Celsius today. Now, to us, if we hear 20 degrees, we're thinking cold. That's snowy and cold and whatever. But this is 20 degrees Celsius, not Fahrenheit. To see what that's going to equal, we put 20 in for C, and it's an order of operations problem again. 9/5 times 20 is 36. 36 plus 32 is 68 degrees. 20 degrees Celsius is equivalent to 68 degrees Fahrenheit. I would take that temperature any day. So now let's take a look at some other conversions. Let's say that we have a car engine that's running at 160 degrees Fahrenheit. Let's convert that into degrees Celsius. We are going from Fahrenheit into Celsius. So we need the formula. We're trying to find the degrees Celsius. So we need the formula that has C equals so that we can convert it into degrees Celsius. That's 5/9 times, in parentheses, F minus 32. So we put the 160 in for F. Order of operations now, we do the parentheses first. 160 minus 32 is 128. And now we have to do the 5/9 times 128. So once again, just 5 divided by 9 times 128. This is going to give us an ugly decimal, 71.11 degrees Celsius. This is where we have to be very careful between the temperatures. If you don't see that something is measured in degrees Celsius, you might be tempted to set a thermostat at 71 degrees. 71 degrees, I mean, I keep mine at about 67 or 68, but 71 degrees is not an uncommon temperature for a thermostat to be set at in the winter. But if it's degrees Celsius, you could be attempting to heat your house to 160 degrees Fahrenheit. That's going to take a lot of fuel or a lot of electricity. Let's say that we have something that is 90 degrees Celsius. We want to see how hot that really is by converting it into degrees Fahrenheit. So since we want to find the degrees Fahrenheit, now we need a formula that is of the form F equals. This is 9/5 times C plus the 32. So we replace C with the 90 degrees, or 90. Order of operations, say we do the 9/5 times 90. What is that? 162, I believe. Something's off there. Let me try. 9 divided by 5 times 90. 810. Oh, I missed that one by a ways. Let me try that again. Something looks a little off there. 162. I was right. Okay, I just punched it in wrong. It is 162 plus our 32 degrees. That'd be our next step. 162 plus 32 is 194 degrees. So 90 degrees Celsius is 194 degrees Fahrenheit. So we do have to be very careful in those temperature conversions from one scale to the other because they are very, very different. Now, if we're using our temperatures in rates, like let's say we have our change in temperature is going up by 8 degrees Fahrenheit per hour. I want to know what is that in degrees Celsius per hour. Here, I do not have to use that formula because I'm not talking about a raw temperature. I'm not talking about a position on that temperature scale. I'm talking about a change in temperature. So I don't need that plus or minus 32 to equalize my 0 point. I just need to know that 1 degree Fahrenheit equals 5/9 of a degree Celsius. Now I should be careful. 1 degree Fahrenheit is not 5/9 degrees Celsius, but a change of plus 1 degree Fahrenheit is equivalent to plus 5/9 of a degree Celsius. So when I do this conversion here, this is 8 degrees Fahrenheit per 1 hour. I have to change my degrees Fahrenheit in degrees Celsius. 1 degree Fahrenheit is 5/9 of a degree Celsius. The degrees Fahrenheit cancel out. We have 8 times 5/9, which of course is going to give us 4.444. 1 hour times 1 is just 1 hour, so that's going to be an increase of 8 degrees Fahrenheit per hour would be equivalent to an increase of 4.44 degrees Celsius per hour. Now again, we're not talking about a raw temperature. We're talking about a change in temperature here. So when we're looking at a change in temperature, a distance moved up or down the temperature scale, we can just use that equivalency because we don't have to worry about the 0 point. Those get tricky. I won't do too many of those. They won't appear on a test, but they might appear in the homework. So you need to know that if we're just looking at a raw change, we don't need that whole long formula. So we are back in the textbook today for homework. On page 154. Wants you to do 1 through 31 the odds. That's dealing with those metric prefixes put on other units like electricity or time or whatever. We have page 156. I'll have you do 1 through 19, the odds there. This assignment, by the way, wraps up Unit 3 for us. This will be the end of Unit 3. Tomorrow we will do review, just because I feel like this unit got spread out a little bit with the days off. We'll do a review tomorrow. Next Tuesday, which is what, October 27th, I believe? Yes. Tuesday, October 27th will be test 3 in class. So be prepared for next Tuesday to be our unit test. That will be officially the last day of week 9 for this class. Any questions? Okay, so we have about 15 minutes here if you want to get started on the homework. I'll be on the network to help you out if you have any questions. Otherwise, if you do want to